In this short tutorial, I will be presenting how particles can be assembled on a 2D substrate using a technique called dip coating. Specifically, we will talk about which colloidal solutions can be processed into ordered particle assemblies, and how convective steering produces tight packed arrangements. Although dip coating for particle assembly is being discussed, many types of nanostructured surfaces can be prepared using this technique. For example, here we see some different morphologies. We have inorganic nanopatterns, which are between 10 and 100 nanometers. We have block copolymers, which are between 5 and 80 nanometers in size. We have latexes. We're going to discuss more systems like this throughout the presentation, which can extend in size between 50 nanometers and 2 microns. And then we have larger structures, such as breath figures, which are between 300 nanometers and 5 microns, which we can see here. Now I would like to introduce you to my dip coater, which you see here in this photo. Dip coating is where we put a substrate into a solution containing normally particles, but could also be solutes, and then either the solvent and the solution is withdrawn or the substrate is withdrawn. And to do dip coating, we have to consider many different parameters, such as the speed at which we withdraw the substrate, the temperature of the surroundings. For instance, in this dip coater, we have a chamber here. We can shut this door, and then the temperature inside the chamber can be controlled. We also have to think about the relative humidity, or the atmosphere, because maybe it's saturated in solvent vapor, which is not quite the same as water. We can also control the solution chemistry. For instance, the concentration of our particles or our solutes, the solvent that we're using, because of course certain solvents evaporate more easily than others, and the substrate surface chemistry, which we can change, making it either more hydrophilic or more hydrophobic. So on our dip coater here, we can see the substrate, which is attached here by a pincher up at the top, and we can see a reservoir here at the bottom, which we fill with the solvent, and this can go up, dip coat the substrate, and then withdraw. Let me introduce some of the deposition forces that are going to act upon the particles to impact the quality of the organization we have on our 2D substrate. In this first example, we see conductive steering, which we'll talk about in detail on the next slide. But we have particles that have been deposited already. We have particles that are coming towards the drying line, and they're brought because there's evaporation here, which then induces a flow of particles towards this meniscus. We also have capillary action, where the surface tension between the particles is less intense than the force on the side of the particles. And so this is going to push the particles together and generate a higher quality of organization. Then we have to think about the withdrawal rate, a very crucial factor for dip coating. There are two regimes that impact the thickness of the meniscus. We can see that as we go from low withdrawal rate to high withdrawal rate, the thickness of the meniscus is going to change. It goes from thick to thinner in an intermediate regime, and then it goes back to thicker again as we accelerate further. We have two different things impacting the thickness of the meniscus. At low speeds, it is directly proportional to the viscosity alone. At higher speeds, it's proportional to two factors: the viscosity of your solvent and the velocity. So these two regimes have different names. Some people call them convective regime here at low speeds. Some people call this the capillarity regime. And some people call this faster speed the advection regime. Others call it the draining regime. But it's the same thing, just two words for the same thing. Here we can see an actual image of convective steering occurring in real time. Here on the left of the image, we can see the assembly of particles. They're tight packed and well organized. Then we see that there's different colors here on the right. This is because the solvent is different thicknesses. So we have different interferences that generate different colors. We see individual particles moving towards the drying line, and we can see particles further out coming in as well because of convective steering. Two things to consider when you're choosing whether or not your particles are good for dip coating are their size and their density. If we have particles that have a very low diameter, typically less than 50 nanometers, or are extremely light, they're going to be blown about in the wind. This is called Brownian motion. They're going to diffuse all over the place, and convective steering will not be strong enough to generate a well-packed film. Alternatively, if our particles are really heavy or really, really large, such as gold particles or other dense particles, the particles risk to have sedimentation forces on them that also combat conductive steering. We need to have our particles stable in solution over the course of several hours in order to have a homogeneous deposition. In addition to sedimentation and Brownian motion, we have to consider colloidal stability. On the left, we see a stable colloid. The particles are individual, well suspended. On the right, we see an unstable colloid where we see certain aggregates. It's impossible to make a nice homogeneous film if we have aggregation in our solution. For instance, we can see in this micrograph that we have several aggregates in the film. We can recognize these because they have a 3D shape to them, where the rest of the film has a multi-layer that's not very well packed. It's all on the same plane, or almost all on the same plane, but they're coming out of the plane. These aggregates make it impossible to have a homogeneous film. You can try as well to recognize areas of aggregates and multi-layer deposition in this film. I'm going to bring up different regions circled, and you can think to yourself, is this a multi-layer or is it an aggregate? And the answer is we have 2 aggregates and 2 zones of multilayer. In blue, we have the multilayer, and red, we have the aggregates. So in your own samples, you can see if you have a problem with colloidal stability. And if you do, there are some solutions. You need to increase the repulsive forces between your particles. For instance, we can have dipolar repulsion at the interface here. This is not what we use when we're doing dip coating. We can have Coulomb repulsion, which is which we can achieve by changing the pH of our solution or by adding salt, which will then go around the particles and increase the repulsions between them. Otherwise, often it's used to add a polymer which absorbs onto the surface, and this creates steric stabilization of our solution. Finally, we need to talk about particle diffusion. So if our conductive steering forces are not strong enough, we won't have a flow towards the meniscus. We'll actually have a flow away. And why do we have this? It's because of the osmotic pressure that increases as the particle concentration increases in the meniscus. So this obviously leads to diffusion away from the drying line. So we have to overcome this osmotic pressure by strong evaporation, pushing the particles towards the drying line. One of the effects that we can use to increase conductive steering is increasing temperature, which increases the evaporation rate. We can see in this example that there were 2 depositions, one at 13 degrees and the other at 17 degrees. Although it may be hard to tell that one is more crystalline than the other, the authors of this paper quantified this by looking at each particle and counting how many nearest neighbors each particle had. At the deposition at 13 degrees, most particles had an average number of 4 nearest neighbors. When the temperature was increased to 17 degrees, however, the average number of particles had 6 nearest neighbors, meaning that this was a much more crystalline system. This was achieved by increasing the evaporation rate during deposition. Another factor to consider is the polydispersity of your particles. Polydispersity is the dispersion in the size of a particle compared to all of the other particles in solution. Typically, when we have polydispersity below 10%, we can have a well-defined crystal structure. There's low impact on our organization. However, if we have between 10 and 15% polydispersity, we'll only achieve a partially ordered structure. Above 15%, the organization will be disordered. We can see this in this example where the polydispersity is lower. It's around 10% in the image B, and we can see that this is a pretty well organized array of particles. However, when polydispersity was increased, the position of each particle is not well defined, and so the structure is considered disordered. To summarize this first part of the lecture, convective assembly can be used to deposit nanoparticles and particles 50 nanometers to 1 micron in diameter, block copolymers between 2 nanometers and 100 nanometers, and dense thin films. Convective steering can lead to densely packed particle assemblies. Polydispersity must be minimized if we want to have an organized assembly. And dispersions must have a colloidal stability of several hours to get to homogeneous deposition. Any flat substrate can be used as long as it's compatible with the solvent. I thank you for listening.